2 years ago, I built my breadboard Z80 computer using an 8-button binary input mechanism to load programs into memory. I am now working on a Mark II variant of my computer, and I want to use a 16-bit keypad along with 7-segment LEDs to allow hexadecimal display and data entry. For this project, I'm going to use common 12mm square buttons, the same ones I use for my ZX81 tactile keyboard that will be the subject of another video. I will mount these buttons on a prototyping perf board. But the key to this project is a 74C922 16-bit encoder, which will convert the signals from a 4x4 keypad matrix into a 4-bit hexadecimal value suitable for displaying on a 7-segment LED. This block diagram from the datasheet shows the basic functionality. Each key press electrically connects one column to one row, and the IC will encode the column-row pair and output it as a 4-bit value. Additionally, the IC will also provide debounce circuitry so that we are not impacted by multiple signals from noisy buttons, and will also properly handle multiple key presses, preventing the wrong values from being encoded. I went ahead and assembled 16 buttons on a prototype perf board into a simple 4-row and 4-column circuit. This will be used to generate a single 4-bit value from 0 to 15. So, to generate the entire 8-bit value, we will require 2 button pushes. Here on the back side, you can see that I connected the first 4 pins using blue wires to the 4 rows. I connected the 4 columns using yellow wire to the second set of 4 pins. It's hard to see, but each column is connected by soldering the pins from each button in the column together. Each button push will complete the connection between one row pin and one column pin. I will go ahead and label the value for each button in hex from 0 through F. To demonstrate the usage of the 74C922 16-key encoder, I will design the circuit in KeyCAD. I will start out with a representation of the unconnected 4x4 button matrix. Next, I will pull in the logical representation of the 74C922 IC. Let's highlight the major logical sections of the IC. First, we have the 4 input pins that will connect to the matrix rows. Next, we have the 4 input pins that will connect to the matrix columns. Next, we review the control pins. First, we have output enable, which is active low. We will tie this pin to ground and leave permanently in the enabled state. As a note, we will add a buffer IC later in the video, which we will use in a practical circuit to control data bus access. The data available pin, which will go high when the key is pressed. The oscillator pin controls the scan rate for cycling through each column. The rate is configurable by varying the value of the capacitor connecting this pin to ground. The keyboard mask pin controls the debounce timing logic, preventing spurious signals from triggering multiple key presses. The debounce rate is also configurable by altering the capacitor value. Based on common usage, we will use a 0.1 microfarad capacitor to drive the oscillator, and we'll be using a 1 microfarad capacitor to drive the debounce rate. Finally, we have the 4 output pins that will represent binary values 0 through 15, depending on key press. To validate the circuit as it currently sits, I will cycle through all of the key combinations. In this next part, I will show you how to convert the circuit to a full 8-bit entry device by adding an octal flip-flop to buffer the data into the bus 4 bits at a time. First, I will add the 74-273 flip-flop to the schematic. Then we tie the 4 output pins to the first 4 flip-flops. Then we tie the first 4 outputs of the flip-flop to the second 4 inputs. And herein lies the magic. When we trigger the common clock, the current output of bits 1 through 4 become the input to bits 5 through 8. Next, we wire the clock to the data available pin. But for timing purposes, we actually want the flip-flop action to occur when the button is released, so we add an inverter between the DA and clock pins. Lastly, we currently have no use for the master reset, so we will tie that pin to VCC so that it never triggers. In this section, I will validate that each entry moves the current key press into the least significant 4-bit nibble value, and moves the current least significant nibble value into the most significant nibble. Now I will wire in a previous project where I used an ATMEL ATF22v10 programmable logic device to convert 4-bit inputs to drive a 7-segment LED displaying hex characters. If you have any interest in PLD programming, I suggest watching my video on the process. Now, I have a circuit suitable for loading 8-bit data onto my bus as I build my next generation homebrew computer. After this video, my next project will be to add a toggle so that I can enter 16-bit addresses onto the address bus, as well as the 8-bit data onto the data bus. This should simply be accomplished by adding 2 more octal buffers, 2 more 22v10s, and 4 more 7-segment LEDs. Design and milling a custom PCB will be the final step to having a front panel data entry device. Thank you for watching this video, and I hope you found it informative.